YouTube tells me I have managed to go live. Very sorry for the delay, guys, folks. The sun outside my window decided to move in some very concerning ways. And I kind of had to like rejuggle my setup so that you could actually see, at least somewhat see me, instead of just glare. That would have been awkward. So took me a few minutes to get that sorted out. So with some delay, welcome back from holiday break. Welcome back to information security, the lecture where we make you feel depressed about the state of information security. So hopefully this actually works. My slide actually works. Excellent. So I am once again stuck in my home office lecture hall, talking into a faceless camera, and hopefully you guys can hear me, because if you can't, that would be awkward. So as usual, there is a Mentimeter link in the YouTube description. You can click that on your phone or on your PC and contribute to the lecture live via these reaction buttons as usual, or you can use the Q&A function if you have questions that you need to ask during the lecture. So without further ado, let's jump into today's content. So as a quick recap, I know it's been a while since the last lecture. As a quick recap, we color technologies in this lecture. So if you see a technology that is highlighted in green, that typically means that the technology is safe to use, that we would, roughly speaking, recommend its use. Meanwhile, if you see a technology that's colored in red, that generally means that you should exert some caution around this technology. It's usually outdated, there's better improvements, there's better choices you could make, and we mostly cover it for demonstration purposes or because it's something you might see in the wild, but we think you might not want to use. Obviously, this is a very quick and dirty categorization, as I say every time. If you want to know why we categorize it that way, well, you should attend the lecture. That's what the lecture is for. It's just to maybe avoid somebody seeing an example on the slides and copying it when it's intended to be an example of what you shouldn't do. Okay, so also recall from last time, I'm not sure I need to go over this again. We have our actors in our threat scenarios. We have Alice and Bob, the two genuine users. We have Eve, the interloper, who wants to attack the system, subvert the system, etc. Alright, first off, let's do some audience interaction, because I need to check how many of you are actually awake right now. So how was your holiday break? This is a quick Menti Q&A, so everybody can open up their Mentimeter real quick and give me some feedback, or you can tell me to stop generating fake engagement, in case that's something you want to tell me, which I of course won't do. I mean, this is a fake choice. I'm going to generate all the fake engagement I want. Right, two of you had to do coursework. I mean, I can't answer my own Q&A, but I mean, somebody had to write these slides while you guys were on holiday break, so yeah, I guess I also had to do coursework. Nine of you wanted another week, and 0 of you were actually had enough of a holiday break. Yeah, that's about representative of what I expected from, well, any student group I polled, really. I don't think many students have ever complained about too much holiday break. Okay. With a fake engagement out of the way, let's move on to the actual content. So last time we had the scenario that you see on the slides. We had Bob communicating with somebody. Bob being a client, Bob communicates with somebody, and without Bob knowing it, the somebody is actually Eve. So Bob tries to communicate with what Bob thinks is a genuine server, potentially, and through some means or another, Bob is actually communicating with Eve. in the lecture we had the scenario where Bob gets an email, clicks a link, and that's actually a malicious email, and now Bob is on a website controlled by Eve. That's the scenario we had. So today we have a obviously different scenario. Today this is our scenario. So today we have us being the web server or the application server, and we have a plethora of users connecting to our application server. And some of these users are malicious. Some of these users are Eve. So last time we always had this kind of implicit solution to the problem. Last time we had the scenario where, well, Bob is connecting to Eve. The implicit solution was always kind of just don't click on weird links. I mean, we kind of talked about how it's an unrealistic solution because there are many different ways in which people constantly have to click unknown links. But generally speaking, there's still this kind of implicit thing where, like, okay, if you just don't connect to Eve, then nothing can go wrong. Well, this time, this is not really a solution, right? Because if you're a web server or an application server of some kind, then usually interacting with unknown users is what you do, right? If you're a web server, then, well, you're usually serving websites to random people on the internet. And even if you're an internal web server, right, you're still serving content to more or less unknown clients. Very few application servers work for specific clients. So you're generally going to get connection requests. You're going to get interaction with unknown clients. And those unknown clients might be Eve, or they might be Alice. Who knows, right? But you kind of have to assume that any client you encounter might be malicious. You can tell because they're an unknown entity to you. Yeah, sadly, attackers do not tend to state their intentions. The RFC proposal for the evil bit is sadly an April Fool's joke and not something you encounter in practice. So clients tend not to tell you that they're trying to hack you. So not accepting connections from Eve is not an option, right? I mean, we need to deal with these connections and somehow deal with them without harming or without inconveniencing or unduly inconveniencing genuine users. So what can Eve actually do though? Because, I mean, I should have probably set this up before going to the slide. Because like last time we had this scenario where Bob visits Eve's website, which means Eve as the server now sends Bob as the client a website. And Bob's browser is then expected to actually render that website, to actually run JavaScript on that website, more or less. So in like this client-server dynamic that we have here, the server is usually the one providing content, and the client is the one consuming that content. So the server has the more powerful of the two roles. So if Eve is the server, obviously, it's fairly simple to see that, Eve has a lot of potential for abuse here. Because Eve can just send JavaScript that does stuff, or Eve can send a website that does stuff somehow. So it's fairly simple to see that Eve can be malicious. But in this client scenario, right, if Eve is just the client, how can Eve be malicious? Well, Eve can send us data. Eve can also send us data if Eve is a server, but Eve can generally only send us data, and then we as a server act on that data. And here we make this distinction for the first time that's going to keep coming up throughout today. So I kind of want to stick on this one for a second. So usually users send us what we're going to call benign data. So data that is kind of playing by the rules, playing nice, playing how we expect it to play. Meanwhile, Eve is going to send us malicious data. Eve is going to send us data that can be arbitrary, can be breaking the rules as we expect them to work can be, well, we'll see some examples. So let's do an example actually. This is an example that was in the news quite a bit if you were watching information security news a few years ago. Right, this slide comes first. We're going to do that afterwards. We're going to do that afterwards. So let's do the example first. So the example here is SSL. SSL is the secure sockets layer. You will have heard this before if you've been paying attention to Maria's part of the lecture. So SSL is the cryptographic technology below HTTPS and many other technologies. So it's sort of a cryptographic wrapper for a connection, if you want. And SSL has many different functions. And the one we're looking at here is what's called the heartbeat extension. So the heartbeat extension is useful if you have, for example, a long-lived connection, where you might have a connection that is idle for seconds, minutes at a time before sending data. And you don't want to keep this connection around if the other side has, for example, turned off their computer. So this heartbeat extension allows either side of the connection to send essentially a ping message and ask the other side to acknowledge that ping message. And the way this this feature works is that the client, or one side of the connection, the requester, sends a heartbeat message, a heartbeat request, which has some unique token, some randomly generated bit of data. And then the other side is expected to send that random bit of data back to acknowledge that the other side is still there and still able to process the connection. So in our example here, by the way, like nothing tells you that stuff's about to go wrong horribly. Like there are being webcomics made about the situation. Like if you ever see a webcomic being made about some cryptographic situation, then stuff's about to go very wrong. Otherwise, people wouldn't make webcomics about it. So yeah, in our webcomic here, which is definitely not about to go horribly wrong, we see exactly this play out. We see our user called Meg sending an SSL heartbeat request and saying, okay, server, if you're still there, please reply with potato. 6 letters long. And the server processes this request, and the server sends back, well, okay, potato, right? Obviously, that's what it's meant to do. Meg tries again. Meg goes, oh, server, still there? Reply bird, 4 letters. Okay. And now because, Meg is malicious, or maybe just an information security researcher, Meg now gets funny ideas, because Meg notices that Meg is specifying 4 letters. And, well, what would happen if somebody were to break the rules a bit? So the rules, implicitly here, of course, are that you're supposed to say how many letters your word has. So if you say potato, you're supposed to say, oh yeah, potato, this word has 6 letters. And if you say bird, you're supposed to say, well, yeah, bird, this word has 4 letters. So there's an implicit rule, or even explicit rule of the specification of the protocol, that you're supposed to say the same length as the data you sent. But as mentioned, attackers get to break rules. So Meg tries a different message. Meg now tries, okay, server, are you still there? If so, reply with hat, 500 letters. And the server, writes this request message in memory somewhere, and then very happily proceeds to read 500 letters, starting at the message it received. And then sends those 500 letters, these 500 bytes, back as the heartbeat message. Of course, the message received was only 3 bytes, hat. And what happens is, of course, that the server reads the next 497 bytes of memory that are not part of the heartbeat message and sends them back to the user, essentially disclosing random memory content. This is called the heartbleed vulnerabilities in information security always have to have spiffy names and logos. So this is called the Heartbleed vulnerability. Is rocked the internet a few years back, and it is a very nice showcase of this distinction between benign data, between genuine data, and malicious data. So in benign data, we would expect there to be the rules followed. So the rule says you're supposed to send the same number of characters as your message. So in benign data, in genuine data, the rule will be followed. In genuine data, the number of letters would be exactly the number of letters in the word. But this isn't genuine data, this isn't benign data, this is malicious data. This breaks the rules in a way that produces unexpected results. So going back to the slide that I skipped. So when we're dealing with data, there are two things we need to do. And one of them is the thing everybody remembers, and one of them is the thing that people forget. So the first one is we need to handle benign data correctly. So yeah, it's a very fancy way of saying your application has to work. If you get benign data, if you get a genuine request from a user, you need to produce the response that is prescribed by your requirements document or whatever. If you get a genuine request for a web page, you should produce that web page. That's the obvious one. Everybody tries to get this right. This is what you've been doing for your entire academic career, writing software that works, right? You've been writing software that's designed to pass the test cases that were outlined by the specification for your assignments, right? You kept changing your software until you passed all the test cases. And then you promptly forgot about everything until the assignment talk was due. The second point, of course, is the one that people tend to overlook. You need to not only handle benign data correctly, you also need to handle any data, even unexpected data, even data that doesn't follow whatever rules you set, safely. So, safely meaning without doing anything that you're not supposed to be doing. Let's say you're not supposed to, as in the Heartbleed example just now, you're not supposed to divulge random memory contents to any client, right? You're not supposed to, let's say, leak user data that somebody's not is supposed to be able to access, right? No matter what data the client sends you, you need to be able to handle it safely. You're not supposed to let the client run random programs on your computer if you want. So this is a pretty important distinction, right? This is a viewpoint that is often overlooked when you're just focusing on getting the business logic to actually work. Getting your program to just pass the test cases. You know, what if an attacker doesn't play nice and doesn't send the data that is specified by the test cases? Okay, so that's SSL. Let's look at the fix, because the fix for these bugs is typically incredibly simple, as is the case in SSL. I mean, if we ignore this bit where they move stuff around a bit, essentially the fix is this one if statement, two if statements. So you have this block of code which is just moved to the middle of the two if statements, and then you have the two if statements. The first and the second if statement, they're essentially just checking exactly this implicit assumption. This implicit rule that says your number of letters should be no longer than the actual length of the message. The fix for Heartbleed makes this assumption explicit. Instead of just the developer assuming, oh yeah, all the data is going to follow the rules, the developer is now telling the computer, make sure the data is following the rules, and if it isn't, deal with it somehow, in this case by just discarding the message. Safely doesn't mean you need to actually react, for example, right? If the data isn't genuine, if the data doesn't follow the rules, right, then you can handle it however you want. You just need to do it safely. You need to not disclose memory content in this example. So in this case, it's completely fine to just say, yep, return 0, just discard the the heartbeat message, because the heartbeat message did not follow the rules. The rules say you're supposed to say the same number of characters as your request. This is the fix. By the way, this code, and I have no idea if this code is still in OpenSSL as is, but this code is an excellent example of unreadable code. If you're a developer that is not intimately familiar with how the OpenSSL core works, you have no idea what this code is doing. These variables called S and P, it's I do this stuff for a living, and I couldn't tell you what this code does without some additional inspection, which is bad. An unreadable code produces bugs, because unreadable code gets touched by maintenance developers who did not write the code. The person who wrote the code 5 years ago has long since left the company. It's left to some poor maintenance developer to fix a bug in that code, and the maintenance developer doesn't understand the code because it's unreadable. And then the maintenance developer introduces vulnerabilities because they don't understand the code, because it's unreadable. So yeah, write readable code, please. This bug was a few years ago, but I really hope that this function is a bit more readable, become a bit more readable in the meantime, because core cryptographic code should not look like this in a production issue, production software. Random ones and twos being added is also not something you should be doing, because it's unreadable. Anyway, my asides aside, let's move on, so we actually get somewhere with this lecture. Yeah, the explicit check right there. Good. All right, let's do some other examples. Today we're going to be doing a lot of examples of stuff you can do wrong, and the purpose here is two-pronged. On the one hand, it further illustrates this point I've been yammering on about, maybe a little bit excessively, about this the attacker gets to break the rules thing, because this is a really, really, really important thing you need to understand. Is the attacker doesn't play by your rules. The attacker can just send you whatever data. The attacker can send you the most inconvenient data possible, and you still need to deal with it safely. But while on the other hand, I also want to give practical examples of things that often go wrong in practice, so that preferably you don't make exactly these mistakes in practice. So we're going to be doing a bunch of examples that actually happen in practice. So one commenter in Menti chat says, I felt the same during P1 of the practicals. I had to look up all these single data variables all the time. Well, yes, but if you're the attacker, right? I mean, personally speaking, if I'm the attacker and I'm looking at code, the more complex, complicated, and unreadable the code gets, the more I smell blood. If I'm the researcher investigating some library or looking at some website for vulnerabilities, the more complicated a website gets, the more weird its JavaScript gets, the more strange things it does, the more I smell blood, because the more I know it's very easy to make a mistake here, right? Vulnerabilities are usually just mistakes that a developer makes. Oversights, right? The developer writing this OpenSSL code just had in their head this assumption that, well, the rules say that the request length, request length sent, has to be the same as the request message length. Surely somebody has checked this somewhere. This is the rules. This has to be true. And then obviously they didn't make the explicit check. And that's how we got a vulnerability. It's always a mistake by a developer ultimately. But we're going to get to this at the very end, but we're all human. We're all going to make mistakes. And we make it harder for ourselves to make mistakes by keeping stuff simple, because we're actually pretty bad at keeping stuff straight in our heads. All right. So yeah, moving on to the first of our plethora of examples that we're going to be talking about today. This is what we're going to be implementing for the next few minutes. It's a bit of a strange example, but not that far-fetched, I don't think. So you are a junior developer at some web design company, and you are given this assignment to implement. So you get a function stub, process order request. So this is obviously some kind of web shop or some kind of order processing system that allows people to send you order requests. So this, you get a request from a client, please order this item. You get this specification of what your input looks like and what your output looks like. So for the input, you're told you get a JSON object that has these values in it. So you have this item ID, which is a number. You have this quantity, which is a number. You have this payment method, which is a string. And then for output, we're supposed to also produce a JSON object with a boolean that indicates whether or not the request was successful. And then we can also return a message that's maybe an error message. It's supposed to be either a string or null. It probably makes sense to have like null if the request succeeded, and like a string if there's an error, whatever. And yeah, we're told implement this, please. This is our assignment. And well, we're gonna do that. First off, a quick aside, since I wasn't actually sure if this is covered in any lecture before this one, so quick aside, JSON. JSON is short for JavaScript object notation. It's a data serialization format. So it's a format that is designed to turn any data into a string. That's what serialization means in this context. So it's supposed to take complex data and transform it into just a sequence of bytes. Some standardized sequence of bytes. It's very, very simple and also very, very widely supported. Practically every language in existence has some form of JSON parser. It's also human readable, which is nice if you're using it for example, configuration files. Its syntax is just a subset of JavaScript's notation for object literals. So if you've ever written JavaScript, this is like what you just, like, this is how you write an object in your code. Essentially just a dictionary for the Python users, a map for the C users, just a key value thing. It supports a very limited set of data types, which helps keep it simple. Just numbers, strings, booleans, DAW, and then you have like arrays, which are just sequence of the above, and objects, which are these key value pairs, and then we have this special null value if we don't have anything there. Okay. Very simple, very straightforward. And now we're supposed to implement this. We're supposed to implement this function. Well, our input is a string, and it says JSON input, so this is clearly some kind of JSON object, right? This is this thing that we just talked about. Well, I mean, this is JSON. This is a subset of JavaScript literal notation. It says so there, right? So this JSON string is just valid JavaScript code. So to turn this JSON string into variables, we're just going to evaluate it as JavaScript code, right? That's what we're supposed to be doing. So this is JavaScript, and we just, evaluate this JSON input and just assign it to these variables, so we have them in nice variables. And then let's just do like a console log. Let's see if this works. We're good, right? Yeah, this evaluates the JavaScript expression. So this just takes some string and just evaluates it as JavaScript code and runs that JavaScript code and then returns whatever the string evaluated to. So you could write like eval string 2 plus 2 and you would get 4. Simple, right? I mean, obviously it's not simple. Like I'm making a bit of a fool of myself for dramatic purposes. Of course, it's not that simple. Obviously, this is an example of a vulnerability, and you're not supposed to be doing this because this works for actual JSON objects. Like if the string is actually a genuine JSON object and follows the rules of JSON objects, then this works. Don't do this ever, but this works. Like if this is a JSON object and you just rapid embrace it, so it's an expression and you just eval it, then you get the object that is in the JSON. That works. Yeah, and then your attacker comes, and your attacker comes by, and your attacker sends you this string, this object. This is also a valid JSON. Well, it's not a valid JSON object, right? because JSON only specifies you're allowed to have, well, these 6 data types. Anything else isn't allowed. These 6 literal data types. But here, we're not just processing JSON, we're actually evaluating it as JavaScript. So if an attacker drops by and sends us this as a JSON object, well, our code is going to evaluate this JSON object, which is not a JSON object, and is going to execute, well, whatever JavaScript code is in there. So in this case, when we evaluate this JSON object, this not actually a JSON object, we're going to run this fetch function in there, which sends our admin password off to some attacker controlled domain, and we lose. It's really that straightforward. So again, we have code that works for genuine input. We have code that works if you're playing by the rules. If the input is actually JSON string, this works. But if the input is unexpected, if the input is malicious, if the input is not a JSON string but actually JavaScript, then it works too well. It does things it's not supposed to do. Yeah, this allows any JavaScript code in the input. That's bad. So what is the fix? Except like the script moving because my screenshot crop is off, but like the fix obviously is just replacing this one bit. Instead of using a function that is designed to evaluate arbitrary JavaScript, we use a function that is, well, designed to just parse JSON objects. This seems really straightforward, but this is a vulnerability that actually happens in practice, right? Because it works. If you're not considering what an attacker might do, then this is functional code. Like this code passes your, like if you just have unit tests that test for proper functionality, right, for everything working when the client does what you expect it to, and this works. This is going to pass every unit test that you throw at it that sends weird JSON objects. This is going to pass with flying colors. It's only going to fail if you write a unit test that says you're supposed to fail if the attacker sends JavaScript, which often doesn't happen. Yeah. So the fix, obviously a JSON parse. This is a function that is designed to parse JSON objects and is going to refuse to parse, well, this weird fake JSON object that has JavaScript in it. Right. It's a bit of a on the nose example, and I'm kind of going out of my way to make the mistake. But still, this is like an actual mistake that you see in practice. People just evaluate JSON code because, well, it's a subset of JavaScript, right? So. All right. What else we got? Next example. We're continuing on our quest to securely implement this this web shop. So we have now successfully managed to parse the input string into variables. And these variables are now, well, variables. They're just the values in the JSON object. Okay. But now we had this console log statement, but like obviously this is a modern web application. Like we can't just have logging to the console. Nobody would do that. No, we're gonna log to a database. Let's go. We have rented an Amazon cloud storage database, and now we need to make use of that. Damn it. So we're going to log our messages to the database. We're going to log this request so we can later figure out if something went wrong, right? I mean, if we find a bug in the code, then we want to be able to go back and exactly see what data did the user send us. We want to go back and figure out what happened so that we can fix it, right? So we do this, which is just like we get the connection to the logging database somehow. Well, helpfully this already exists. Excellent. And then we have made this order log table. This is like, yeah, we have like these columns. We have this item ID, the quantity, the method, the user IP. Okay. And then we stuff in the item ID, the quantity, the payment method, and the user IP. Simple, right? Again, we have a quick aside because I'm not sure if this is technology that you have officially been introduced to, so we're going to very quickly talk about it. This statement, of course, is using SQL, the structured query language. You have almost definitely seen SQL statements before. They look like this. They're actually pretty readable. Yeah, most widely used database language by far, to the degree that I'm actually not familiar with any other. Like, there's variants of SQL, like different database servers use slightly different dialects of SQL, but apart from very minute details, more or less is the same language. So it's this human readable instruction string that we just send off to the database engine. So we take this instruction that says insert this data into a table called order log, and this table order log has these columns. The columns are item ID, quantity, method, and user IP. And in these columns, you're supposed to insert the values 18,000 whatever, 25, PayPal, and this IP address respectively. This is what this instruction is telling the database. And that is what we're doing here, right? We're just building exactly this query that is in the image. We're building this query out of the input values. We're taking the item ID, we're taking the quantity, and the payment method, and the remote IP address, and we're just putting this in the string. It's one long instruction string. And then we're sending this off to our logs database. Be good, right? Like, I mean, obviously we're not good. Like, it's just I need to keep I need to keep pretending there's tension. Like, obviously we're not good. So this payment method is an arbitrary string, right? Like an arbitrary string that Eve gets to choose. The attacker gets to choose. What happens if there's a quote in there? Huh. That's awkward, right? Because we have this SQL query, this instruction to the database engine, that is just a string. Like, this is just a long string, and all the data is in this string, and all the instructions are in this string, and this is all one big string that is parsed by the database. So if there's a quote in there, then this is no longer just data. This payment method is no longer just data that gets inserted into the table. But suddenly, Eve can write database instructions for our database. Let's have a look at what happens. So this is the query. This is this query that we're executing. This is just this query copied one-to-one. And now Eve inserts this weird string in the payment method. This weird, like, there's an escaped quote. The backslash just escapes the quote because the quote is also used in JSON. So the string just has this quote, and then there's a double quote, and then it closes the braces. Oh, that looks weird. Let's see what happens. So we insert this where it says payment method in red. The red stuff is the stuff Eve puts in. Oh, that looks like SQL. That is SQL. So Eve is like, let's say we're finishing the genuine statement. Like, we have this weird half statement where we have like values, item ID, quantity, and then the payment method. So we're finishing this weird half statement with like the quotes and then the quotes. So everything is like, there's values that are expected. And then we have the second query in the string, which is updating the accounts table to set the admin flag to 1 on Eve. Huh. Well, that's not supposed to happen. So here we have, well, the header spoils it. Vulnerability that I think all of you will have heard about before. It's probably the most widely known class of vulnerability, just because of how old it is, really, is called SQL injection. So this is injecting SQL instructions into a string, and that string being concatenated into a database query. So this can happen whenever you put random user strings in your database query. Now there are fixes, countermeasures for this vulnerability. And the obvious one, perhaps, is to take the user string and just sanitize it. Remove anything that looks dangerous. So this is the I want to say older, original countermeasure to SQL injection. You just look at the user string and you just escape anything that looks dangerous. So any quotes, any single quotes, any double quotes, any dashes, any funny business just gets escaped with a backslash. So that when it gets concatenated into the string, instead of being an SQL statement, well, we just have this escaping backslash in front of the quotes, and then this is all part of the actual string, and then the query is fine. Now, I marked this red. Don't do this if you can help it. Why? It's very hard to predict every value that could be potentially dangerous, because strings are complicated. I mean, you might now think, well, okay, just escape like quotes and stuff, and like single quotes and double quotes, easy, right? No, because what if your string is not encoded in ANSI, where everything is 1 byte, but your string is encoded in UTF-8, for example, where a single byte might change the meaning of the next byte? And you have like 1 byte that is part of the attacker string and 1 byte that is part of your original string, and you concatenate them and suddenly it means something different. There's actual vulnerabilities like that like circumvent SQL escaping by abusing UTF-8. Pretty cool. Also, as previously mentioned, we are all human, we all make mistakes. And it is incredibly easy to just miss one time that you're supposed to sanitize the string. Because obviously if you're trying to sanitize or escape input, you gotta do it every time. You gotta remember every time. And it's very easy to miss that you didn't. Because if you forget to escape your input, it's still gonna work. Like, if you don't do any escaping in this logic, again, it's gonna work. Like for genuine user input, this works. Assuming there's no quotes in the payment method. But then again, like the payment method here is probably like a fixed string. Like it's the result of some multiple choice thing. Like you have a drop down where it says like PayPal and MasterCard and Visa and whatnot, right? It's like a fixed string, there's no quotes in there. So for genuine data, this works. Like, this isn't gonna fail any test cases. It works. So it's very easy to miss that you didn't escape a certain field because, well, it's still gonna work. Nothing's gonna scream in your face and go, oh, you missed a thing. I cannot compile. Wait, you can compile. It works. It's still broken, but it works. So yeah, hard to predict every potentially dangerous value. Easy to miss subsanitation. Because you forgot once. So this is the old solution. This still is widely seen in practice. And I have broken web applications that forgot to escape exactly one input value. Like actual real life web applications. They were properly escaping almost everything. And then they forgot one multiple choice value. And suddenly I could read their entire database because that's what SQL injection does. Or change their entire database, but I'm not mean like that. So, yeah, very hard to get right in multiple ways. So don't do it. There are far better alternatives. Modern database engines support what's called parameterized or prepared statements. Essentially, we're going to see an example in a second. It separates instructions and data. So in these previous SQL statements, we had this thing where we essentially intermix the instructions. What is the database engine supposed to do? So insert something into a table, into these columns of the table. That's an instruction. That's telling the database do what, do an insertion. And the data, like the actual values it's supposed to insert. Semantically speaking, these are not the same thing. And the flaw that is being abused by this SQL injection vulnerability is that we can confuse the database server. We can take what the developer thinks is just data, is just string values, and by choosing the right string values, we can make the database think that this is instructions. We can make the database think that this is actually this update statement, which the developer never intended. Like, if you're thinking about this in terms of a programming language, like, this is insane, right? Like, this is you calling, let's say, okay, print is a bad example because we all know how very insecure printf is, but let's say this is you calling a function that says, you know, I was gonna use log here, but in light of recent events, maybe that's also not the best example. Well, this is you calling a function that says, what's a good example? I'm actually not sure. I was sure I was going to use log here, and then I realized that log4j just happened, and maybe that's not the best example. But let's go with it anyway. This is you calling a function that says log output. Just like write some string to the console. But if you specify the right string, then that function suddenly leaks your admin password. It's like strange, right? You're not expecting, when you call a function A, you're not expecting to suddenly be calling function B just because it's the right string in there. Like, it's not something that's supposed to be happening. Like, it's generally not something we design functions to do in the modern day and age. If anything, is like relics of the past, like printf that let you do that kind of stuff. It's like you're by specifying the right data, we end up with instructions. That's weird. So the fix, of course, is to just semantically separate these two. These are different things. Instructions are not data. Data is not instructions. And we can just tell the server, these are the instructions, and this is the data. Like, we can do that. We can just send them separately. That is what prepared or parameterized statements do. First, we have this fixed string. So this is safe. This is this fixed string that we choose, where we parse the database server parses the string to determine what it's supposed to be doing. It parses the server to go, okay, I'm supposed to insert data into order log, into these columns of order log, and the values I'm supposed to be inserting are these placeholders, words. So these question marks, these placeholders, is where the data goes. And then we run this statement and we separately specify the data. We separately specify, oh yeah, where the question marks are, fill in this data. This item ID, this quantity, this payment method, and this remote IP address. And now we're communicating to the server, this is data. And then the server doesn't even look at it as SQL. It just says, oh, this is a string. I know how to deal with a string, and just puts it in the database. And it doesn't even parse it as SQL. So we just completely avoid this vulnerability because we go out of our way to actually separate instructions and data. We make it hard to mess up because it's incredibly hard to mess this up. If you're always using, and you should be, if you're also always using prepared statements, if you're always using these parameterized statements, and you're never, ever, ever using an SQL query, an instruction, stuff that goes in prepare, that is not just a fixed string that is built from user input. You always just use fixed strings. It's incredibly hard to mess this up. Like, it's, as opposed to the SQL escaping the sanitization approach we had just before, where every time we take user input, we need to remember to sanitize the user input before we concatenate it into a query. Very easy to mess up, just have to forget once. This is extremely hard to mess up, right? This is very, very misuse resistant. As long as you have a fixed string in your prepare statement, then whatever you put in the parameters is safe. You can put anything in there and, well, nothing bad's gonna happen. I mean, it's not actually true. Like, if your parameters have like 20 terabytes, then you're still gonna have a 20 terabyte database, but at least you're not vulnerable to SQL injection, is my point. So yeah, foolproof, almost. Misuse resistant is what we're gonna call it later. This is why this is green and the other one is red. Like, both of them, if done properly, fix the issue. Proper string escaping fixes SQL injection. But it's hard to do proper string escaping, and also it's very easy to forget to do string escaping once, and that's all it takes. So use prepared statements. Every language in existence supports these in 2021. Like this technology is out there. Use it. And also it makes your code faster, funnily enough. Right. See, this is like a very lengthy coverage of a single example of code injection. Code injection is not an SQL only issue. It's an issue that's going to happen anytime that you communicate with another program in just strings. Like anytime you encode instructions in a string, you have injection issues. Because again, if you concatenate user input, then that user input that you think is data might actually be instructions. So this happens in LDAP if you do search strings for certain users in an LDAP directory. XPath, the language for specifying XML lookup paths. SOAP is a good one. That's a authentication or an API framework that communicates in XML. It's really popular. If you do bad things with user input, then suddenly you end up with an XML syntax in your user input. XML in general, XML files are very vulnerable to this kind of thing. Java object serialization is a big one that I forgot to put in the slides. Java lets you serialize and deserialize objects, similar to what JSON does. But Java not only has these like static data, but Java also serializes bytecode. So program code to be run on that object, essentially it's not just serializing the data, but it's actually serializing the entire object, the entire data type, including any methods. If you manage to inject Java bytecode, then suddenly your methods no longer do what they're supposed to be doing. That kind of thing. Yeah, and it's always the same countermeasures. Like that's why I'm not going over every single one of these in detail, because the countermeasure is always the same. Either make sure that the client, like the input string, is sanitized, so there's like no dangerous stuff in there, or semantically separate it somehow. I mean, I say we're not going to look at these examples. We're going to look at one more class of problems, potentially after the break. I've actually been taking a lot more time than I thought I would in these slides. So yeah, who else communicates in strings all the time? A web page with the browser. Like when you request a website, you're getting text. You're getting a text file. You're getting a text file that is formatted somehow in HTML. This markup language, which we discussed last time, this markup language that describes a website. And then your browser interprets that markup language and, well, renders the website according to what the HTML says. And, well, what did you just say? Whenever we communicate instructions in strings, we have a potential injection vulnerability. Yep, let's go. Let's look at the first example real quick, and then we're probably going to go on break. So the first example here is PHP. I don't want to shit on PHP here, even though there are many reasons to shit on PHP 4. But it's just a very popular language, so it's the one I chose. So here we have a program, the website that displays a private message. So this is some forum software, maybe something like that, something that lets you send private messages. Okay, so the user makes a request to this website and this PHP code runs. And because we've listened to information security, so we know that we're supposed to be using prepared statements. So we are going to use a prepared statement. We are going to prepare the statement that just says, okay, select the sender, the message, and the recipient from this table called private messages, where the ID is whatever the placeholder says. And then we are going to execute this prepared statement specifying the ID that the user specified. Ah, good. We're escaping user input. Excellent. If we were to just concatenate the user input, this would be an injection vulnerability. But we're smart. We're using prepared statements. So whatever the user puts in the ID, no SQL injection. Excellent. And then we're going to execute this statement, and we're going to fetch the first result. And if there isn't a result, then, well, we just say not found. Well, no message with that ID. We're also smart. We're going to do an access check. We're going to check, oh, is the recipient actually the current user? And if not, well, you're not supposed to read this message. And then, well, okay, we've done our access checks, so let's actually print the message to the user. So we have this private message with the sender, this message, this recipient. Now we just need to output this, right? Simple, straightforward. Let's write HTML. So we do like this HTML stuff. We do like head, title, whatever, body, h1, new private message from, well, whoever the sender is, and then we just output the message and we're done, right? We're obviously not done. Like, I'm gonna keep doing the theatrics, but we're obviously not done. So what happens? This is a string, right? This is an HTML file. HTML files are just strings. What happens if we put unescaped, unsanitized user input in strings? Injection vulnerability, see what happens. So let's look what Eve is doing real quick. So Eve sends a private message. Eve registers an account in a forum, sends a private message to a victim. And the message says, sorry, nothing personal, kid, and includes a JavaScript tag. Oops. And what happens? Like, I'm gonna skip through this because we're a bit late on time, and also, like, you've seen this pattern a few times by now, you will recognize it. So what happens if we take this PHP code here, and we insert the message up there. I'm pointing at my screen, you guys have to imagine that I'm pointing up there. Hold on. If we take this PHP code up there, and then insert the message all the way up there, something like that. I think that was roughly where the slides are on your screen. What happens? Well, we just insert this message, including the script tag where it said insert the message. Oh, and we end up with valid HTML, which includes a script tag. Awkward. Right? We have this fetch request, which sends all of our cookies to the attacker. And as you might recall from last time, if we lose our session cookie to the attacker can impersonate us. That's bad. Yeah, also, as you might recall from last time, we discussed last time this powerful browser safeguard called the same origin policy. And essentially what same origin policy does is it prevents scripts, JavaScript, from accessing data that is originated by a different origin. So we said last time, even if Bob visits Eve's page, even if Bob visits evil.org, any JavaScript that is sent from evil.org cannot read any data that comes from genuine.com because they're different origins. If you use a different scheme, so either HTTP or HTTPS, if you use a different one, or if you're on a different host name, or if you're a different port, then you're a different origin and you are untrusted and you don't get to read this data. So even if evil.org tries to read genuine.com's data, it cannot because of the same origin policy. Well, but this script that Eve managed to sneak into their private message, this is now being sent from the victim website's origin. This is no longer being sent from evil.org. This is now being sent from genuine.com. So this gets to bypass same origin policy. Like this is a script from the website itself. Like this was sent by the genuine web server. So this script gets to bypass same origin policy, gets to read the document's cookies, and gets to send them off to evil.org. And this is why, like, this is the impact here. The impact here is that we're getting a different website. We're getting the victim website to run our JavaScript. Instead of tricking Bob into visiting evil.org and then running our JavaScript, which is restricted by same origin policy, we're tricking the target website into giving Bob our JavaScript. We're tricking the website into bypassing same origin policy for us. So yeah, this is called cross-site scripting. Shortened to XSS because everything needs to have an acronym in computer science. Otherwise, we could not pretend that we're so good at our jobs and nobody understands them. And CSS was already taken by cascading style sheets, the thing that describes how web pages look. So it's called XSS. something to keep in mind. So yeah, we're tricking the target website into sending, or the victim website, we're tricking a website into sending JavaScript to our target, which lets the JavaScript bypass SOP, meaning it can read session cookies, request authenticated resources, read passwords, send itself to other victims, anything. Like, the moment you're running JavaScript in the context of the target website, you pretty much win. So yeah, that's bad. Countermeasures. Yeah, you've seen this before. String sanitization and semantically separating instructions and data. Yeah, it's always the same countermeasure with these things. Like, it's always the same stuff. Either you make sure that the string is secure, or you make sure that the string cannot be confused for instructions. Those are the two options. Let's see what the next slide says, and then we're maybe gonna break. Yes, the next slides we're gonna talk about countermeasures to cross-site scripting, because it is also one of the most widespread vulnerabilities on the internet. We're going to talk about countermeasures. We're going to talk about how to not allow cross-site scripting. I'm going to talk about why it is so incredibly difficult to avoid cross-site scripting, and things you can do to, well, mitigate that. It's a bit of a cat and mouse game. So yeah, that's after the break. For now, we're going to break, not for too long, because, well, we still have content to get to. So we are going to break for slightly less than 10 minutes. We're going to break until 10:45. So that's in, should be roughly 8 minutes. We're going to reconvene then. And then we're going to talk about countermeasures to cross-site scripting and, well, more, because I have a bunch of more stuff I want to talk about. So yeah, see you in 7 minutes. Grab a coffee or something. And I'm going to mute myself. mic button. There we go. Excellent. Yeah. Turns out the clock in the other room is off by a minute. That's on me. Alright. We are back with information security. Still the lecture where we make you feel depressed about the state of information security. So, yeah. As promised before the break, we are going to talk about countermeasures to cross-site scripting. And we're going to talk in particular about the second point, because the first point is perhaps unsurprising. String sanitization is the same as it is always. You just escape the stuff that looks dangerous. So how do you semantically separate instructions and data? Because it's not immediately obvious. Before the break we had this PHP file. And if you look at it from this standpoint, where you have this script which essentially generates HTML output and then sends that HTML output to the user, and that is the only way you communicate to the user. You only communicate to the user once by sending them this one file. It is not immediately obvious how you semantically separate instructions and data here, right? Because anything you send is part of this text HTML file. So anything you send, if it isn't sanitized, could be used to produce HTML output, right? It's not clear how you would escape, or how you would separate the data here from the HTML. Of course, the solution is by communicating more than once. So this here is what that should look like. So here we have, again, a website, but this time the website is static. This is a static website. This doesn't have to be dynamically generated by the server. And what does this static website do? Well, first at the bottom, we're going to start at the bottom. And at the bottom, we're going to see this HTML document. This is not valid HTML, by the way. For readability, I moved the JavaScript to the top. Obviously, the JavaScript should be inside the HTML somewhere, but I moved it out because it's more readable. So at the bottom, we have the HTML document, which is this head, title, body, same as before, pretty much, exactly the same as before. But instead of having these dynamically inserted data, which would require escaping, we now just have empty container elements with some ID assigned to them. And then we have this JavaScript. What this JavaScript does, let's see. So first we have this first line, which something ID. If you don't want to follow that line, just assume that it extracts the ID from the URL. We check that it's a number. Okay, that's useful. Check it's a number. If it isn't a number, then this is invalid. Okay, and then we make a request to the server. And now we see where this separation comes from. So first we have the instructions, which is the HTML, right? The file, the HTML file, the JavaScript. This is all instructions. This is all code. And now we fetch the data. So first we have send the instructions, and the instructions are separately going to fetch the data. And the data is what's user provided, right? So the instructions are fixed or static or safe, and the input, the user data, the dangerous part, is now fetched separately. So we fetch this query dm PHP URL, and this query dm PHP URL essentially does what the PHP stuff in this script did. So this essentially just does exactly this query where it fetches the data from the database and does the access check and stuff. This does exactly the same stuff. Wait, this is too far forward. Here, this is where we were. So this fetch thing does the same thing that our script did before on the server. It fetches the information about the DM and it returns it in some serialized form. We're going to assume that it's JSON here because we already talked about JSON. So essentially you get back from the server a JSON object, structured JSON object, which contains the information about the message, in particular the sender, and the message, the body. And then you simply tell the JavaScript, okay, take this response, check if it's successful. If the response message is like 404, for example, not found, then we report this error somehow. And if it is successful, then we parse it as JSON. And once it's parsed as JSON, we insert it into the document. So we take the sender, we take the message, and we put the sender and the message in the content where it's supposed to go. And here we have this semantic separation of instructions and data, right? The instructions are the JavaScript file, the HTML code, and the data is now being loaded and then processed safely as text. So no matter what the sender says, no matter what the message says, it's just going to be inserted as text into the HTML document. And then something error handling. I didn't have it here. Also at the top there's a note says this should be a separate file. Yeah, this should definitely be a separate file. I've made it inline here because it's more easy to read. But like JavaScript should always be in a separate file, and you should never put JavaScript inline if you can help it. We're going to talk about why in a bit. So yeah. Next we're going to talk about a few gotchas with cross-site scripting, because this sounds simple, right? Separate instructions and data. Straightforward, right? Just static file and then request data from an API and then do stuff. Simple, straightforward, impossible to get wrong, right? Very easy to get wrong. Let's look at another example, very similar to the one from earlier. This one, well, a bit different. So before we had a single direct message. We sent an API query for a single direct message, and we inserted that single direct message. But now we have something different, because now we have this API that's called query DMs. I still have an ID stuff in there, which is a copy-paste error that's not supposed to be there. But we have this API that does query DMs. So this is like maybe a list of messages or something. And we query this API that says query DMs, and we get back a JSON object again, and we parse it. And now, instead of having a single message where we just insert the sender and the message where it's supposed to go, we now have a list of messages. We have a JSON array. This data is now a JavaScript array, and this consists of these sender and message pairs. And what our job is now is to add a new entry for this direct message to the container. So we have this message list container, and we're supposed to put our direct message link in there. So there's no like predefined element where we can put the content, but we need to make a new element. That's the difference. Because like there's no predefined, like in the HTML, there's no like list elements. That's just a list container, and the JavaScript is supposed to put the list elements in there. Well, how do you do that? Straightforward. You just do this. You just do like, okay, this container, this message list, and this has this useful function called insert adjacent HTML, which just lets us insert HTML at a certain position in the code, right? For example, here we say, okay, just insert this HTML before the end of the list. So just at the end of the list. This HTML, yeah, looks good, right? Like this is a link, this ahref is a link to the message PHP file for the message. And then we have the sender name, okay, yeah, from whoever, and then we have the subject, and we put the subject in there, and then we're done, right? Like we have this very simple, straightforward layout where we have like, hey, from, well, backwards, from Alice, hi. It's like what this looks like, and then like the entire thing is a link, and if you click on it, you go to the message page. Simple, right? What could possibly go wrong? I mean, everything can go wrong, that's why we're here. So, what goes wrong? Well, the same thing as always, but people still forget. What happens if you interpret user input as instructions? Cross-site scripting is what happens here. Yeah. So we take the sender and we take the subject and we put it in the string, and then we say to the browser, please interpret this string as HTML. Well, isn't that awkward? Exactly the same vulnerability as before. Like, the point being that, like, this separation of, oh, we first have the static code and then we fetch the user data separately is nice, but it's not a magic bullet. Like, you still need to be careful what you do with the user data in JavaScript at that point. Because here you're taking the user data, or it's unfair to say you, I should say I'm taking the user data, and I'm using it as part of a string, and then I'm telling the browser, please parse this string as HTML, and then of course everything goes to shit because, well, you parse this HTML and it's user input, so it can have whatever in there. Exactly the same vulnerability as before, just in a different color. Yeah, other ways to make the same mistake. The reason I keep harping on about this is that I have broken too many websites by exactly this technique. They do fancy API stuff and they don't do PHP, and they have static websites and everything, and then they use jQuery's.html function, and suddenly there's a light bulb above my head and the website is broken. Or they use jQuery's $$ function, which also parses HTML, or they use .inner HTML, which modifies the HTML contained in an object, or any of the hundreds of ways you can get HTML content into a document using JavaScript. I'm not going to list them all because that would be exhausting. So anytime you parse user input as instructions, HTML is instructions, you have an injection vulnerability. Here, you have an injection vulnerability. All of the bullet examples, you have an injection vulnerability. Never parse anything as HTML except as static string, fixed string that you specify, no user input. Yes, I'm going to keep harping on about it because people keep making this mistake. How do you do it? Like this. A bit more lengthy, but secure, which is good. I meant to have a slide that didn't have the thing in the way. Oh well. So what do? So we compare the two. Here we have this loop over ID, sender, and subject. That's the interesting bit. Everything else is the same. And in the original, in the broken, hold on, I need to point somewhere else. In the original, something like that. In the original broken code, we had this HTML string which was dynamically generated from user input. And in the fixed version, we have this static HTML string. This is static. This is not subject to user input. This is just stuff we put there. It's safe. And then we insert this entry into the document as HTML because we're lazy and we don't want to type document create element 4 times. That's why we're doing that. We don't want to like manually insert elements. You can also manually insert elements. Like I always manually create and insert elements in my web applications. But I also know that people don't like doing it because it takes a lot of typing. So you can do this, but make sure the HTML is static. And then we do the same as we did with the single direct message before. We then take this newly created element by using last element child, and then we just assign the link, the sender name, and the subject using JavaScript as text. Again, the inner text bit is important. We're assigning it as a text value, which makes it safe. No matter what's in the subject or what's in the sender, if we're just changing the text, we're telling the browser this is text, this is not HTML, don't parse this, don't process this, just put it there as text. Now it's safe because we have this separation of instructions and data. Yeah, that is that. Also, a quick word of note. I didn't talk about the ID because this is coming from the server. So I'm assuming that the server is actually a number here. In our JavaScript, we get to assume that the server is playing by the rules. Assuming that the server does the necessary checks, of course. So here I get to assume that the ID is a number because I'm assuming that the message was generated by the server, which sends a number. But of course, trust but verify, you could and probably should, well, should is a bit excessive. You could verify that the ID is actually numeric here. Though, again, you wouldn't have XSS, like this is just the href thing, but you want to make sure that, for example, the attacker cannot change the URL that you're linking to, by like some crafty shenanigans with the ID, making you link to a malicious site or something. Could be a potential attack vector, so yeah. Just something I just noticed as I read my own code. Okay. So yeah, again, we have this thing that I keep harping on about. We have the separation of data and instructions. Instructions is static HTML. And then the dynamic data, the stuff that gets loaded, that user input is used as text, so it's safe. Another example, this is some kind of search functionality. This is like some search page. So we have this query parameter in the URL. So we have this query, which we get from the URL, this Q parameter, and then we do an API call again. We look at the search PHP API. We send the query body again, the query value from the URL. And if the response is okay, then we parse the search results and we insert them securely into our list. This time we're using jQuery. We insert it into our list. The reason that a lot of these, by the way, use like different frameworks and different languages is that a lot of these are like derived from actual vulnerable code that I've seen in the real world. That's why like this one uses jQuery and the last one uses like vanilla JavaScript, because they use those in practice. And then we set the search query to some string, and then we assign a class name to like make sure that the error messages are shown or not shown or whatever. And of course, like, I mean, at this point the lecture, I don't need to tell you where the vulnerability is. Everybody can see the vulnerability. It says .html. .html is bad. It parses user input as HTML, which is bad, which is a vulnerability. Hold on a second. But what is this user input? This user input is the search string. This user input is this Q parameter. That's where the query comes from. Like, this query isn't being sent by some other user. Like, before we always had these private messages, right? Where some other user is sending me a message. So some other user might send me malicious code. But like, this is myself. This is me attacking myself. What? This query is a thing that I put in there. Where's the vulnerability? Aren't you being paranoid? I mean, no, I'm not being paranoid, or I wouldn't put the question in my slides. Recall from last time, before the break. What can Eve do if Eve is the server? Eve can navigate Bob to arbitrary URLs. We have this example here. secure.lawful.org, create admin account. And then we said this is called cross-site request forgery, and it's harder with the same-site lax default, and blah, blah, blah. And then we said badly designed websites might still be vulnerable. Funny how that works. Yeah, never let get have side effects. That's not what we're doing here. Never trust URL parameters, even from trusted users. Haha. Yeah, that's this. This is the thing that I talked about last time. Even if it's Bob sending, sending the query parameter, even if it's the user themselves sending the parameter, then you still have this problem because, well, the user might be sending the parameter, but the user might not know this. For example, here we have an example of this attack where we have Eve sending a link to Bob, or redirecting Bob to a website, and Eve is redirecting Bob to genuine.org, to the search URL that we're showing here, and the search query parameter URL encoded is a script tag, which calls the steal all the data function. If your website has a steal all the data function, then reconsider your website design. But generally speaking, it's an example, of course. So yeah, here we have Bob being attacked by Bob's own query string, because the query string was crafted by Eve. Now you might think, oh, but I would never click on a link that has a script tag in it. I'm not dumb. At which point I have to ask you, how often have you clicked on like a bit.ly or a g.co or any other link shortener in the last few days? You have no idea where it's redirecting you. You have no idea if it's redirecting you to genuine.org with a query parameter that's JavaScript, right? So anybody that's ever clicked on a link shortener in the last few days, doesn't get to raise that defense. Besides, I don't believe in it because people don't understand hyperlinks and they're very used to 5-line hyperlinks in verification emails. Nobody reads this. We have a question from Q&A actually. Can you disclose any example of a service provider which had these kinds of vulnerabilities? Is there a typical class of service provider that implements these kinds of vulnerabilities? I mean, I can give some examples because those are public. I did my master's thesis on security vulnerabilities in online learning apps. So a bunch of those. You can find my thesis in the university library if you feel like it. It's even accessible as a PDF online. Typical class of provider that has these vulnerabilities. I mean, there's classes of providers that won't have them. For example, anything that is subject to auditing requirements, for example, any like payment processors, stuff like that, probably won't have like simple XSS vulnerabilities or simple SQL injection vulnerabilities because they're subject to auditing requirements. So they're required to have like professionals looking at their code. It's called penetration testing, or also called red teaming in less formal lingo. Essentially, you have a group of people or a person whose only job it is to pretend to be an attacker, to look at your code like an attacker would and try to break into it. And that finds you vulnerabilities, and when you find them, you fix them, being the thought process. And anything like any large company that has auditing requirements, that has to have certain security standards that they have to meet, is going to have that kind of setup, at least using like external suppliers periodically to have a look at their code and have a look at their website and try to break in. So they're not going to have this kind of like trivial XSS stuff that we're showing in the lectures. That doesn't mean that they don't have XSS. I don't have a quote offhand, you'd have to find this yourself on the internet, but for example, I recall an example of a researcher firing off blind XSS payloads in certificate requests, HTTPS certificate requests for certificates. Essentially putting cross-site scripting attacks in description, for example, the description field of a certificate request, and firing that off to just a wide variety of certificate authorities. And the JavaScript essentially, when it executed, it just gathered a bunch of information about the current environment, the current browser. It took like a screenshot, and it gathered all the script files that were running and just sent that off to the researcher. And the researcher fired those off and kind of forgot about it, and because didn't think much of it, but worth trying. It doesn't cost you much if you already have the setup for it. And the researcher ended up, for example, getting cross-site scripting in the internal admin control panel of at least one certificate authority. Like their public-facing software, their public-facing websites were like pristine and audited and everything. But like the shoddy internal use-only cordoned off inside many firewalls admin control panel, which displayed fields from the user's certificate request, string fields, wasn't so secure. Probably wasn't audited, and because nobody thought of it, like it's not public anyway, what's going to go wrong? So you end up getting cross-site scripting access in the control panel of a CA, which of course can lead to problems. Because like the moment you have JavaScript running in the site, obviously you can do whatever you want For example, your JavaScript, you could, now that you have initially infiltrated the CA and you have gathered all their JavaScript that runs locally, you can now look at the JavaScript and craft your own new JavaScript implant, which, for example, automatically approves your certificate request. So you could send a certificate request for google.com, and in the free text, in some of the free text fields, like the organization field or whatever, you put a JavaScript link or a JavaScript embed that essentially just clicks on accept. And then, assuming that the internal processes for the CA are sufficiently lax, you might get a valid certificate for google.com. Of course, assuming that there isn't a second person that has to approve the request, at which point you would probably be noticed. Because like that would raise internal red flags when a phase 2 reviewer finds a google.com certificate that was approved by phase 1. It would probably raise some question marks. At some point, somebody would look at your certificate request and realize, oh wait, there's an XSS payload in there. But like the researcher obviously didn't try that because people are good and also they like back bounty money. But like in public facing stuff, you're less likely to find that kind of vulnerability. You're less likely to find obvious vulnerabilities in these big audited companies, like big entities that have auditing requirements are less likely to have this kind of vulnerability accessible easily. Anything that's like open source or hobbyist or otherwise unconstrained by things such as auditing requirements, code review policies, that kind of thing, unconstrained by concerns of, oh, if this goes wrong, then I'm looking at at monetary damages, like the way a corporation thinks, right? Like the way you motivate corporations to do things is money, as always, and potential damages from a data breach is a great way to get companies to invest in cybersecurity. Like you're not going to get them to invest by saying, oh, you have to protect your user data. That's just the right thing to do. But if you say, well, but if you don't protect your user data and you are found to have acted recklessly in disregard of common industry standards, then you're going to be liable for any damages incurred by loss of your user data. Then suddenly companies become very interested in cybersecurity. So for that reason, all of this auditing business exists, and you're unlikely to find these trivial vulnerabilities in big companies. But anything that isn't constrained by such requirements, because, well, your code ships with a license that says, oh, I disavow any damages, this code comes with no warranty, and if you use it, it's your fault if it breaks, then your hobbyist project obviously doesn't concern itself with such requirements. At that point, you obviously have a lot more potential for this kind of vulnerability slipping in. A lot of these examples are taken from my work for my master's thesis, which was on education apps, which tend to be like more or less hobbyist projects run by like small teams of a few people. Like often they're like trained educators. They're not even like trained web designers. They're like trained educators that happen to have some web design knowledge, putting together an application, and then things go wrong. But yeah, that's that one. Your camera focus seems a bit off, at least for me. That's bad. Oh yeah, my camera focus is off. I'm not sure how I can fix that. Like this is supposed to autofocus, I think. Did that fix it? No, it doesn't seem to autofocus on me back here. Let me see if we can change the lighting. Does that make it better? It just makes the light weird. Is that better? I can barely tell because I know, yeah, this looks good. Just looks better. Let's leave it like that. Let's leave it like that. Okay, so you can actually see me. Sorry about that. Yeah, the lighting is a bit off today because the angle of the sun is weird, because like the last time I used this setup, it was like a month ago almost. So the angle of the sun was slightly different, which makes it awkward. Alright, let's leave it like that. You can see me now, I hope. But yeah, like there's no clear like rule of like, oh, this kind of this level of company would never introduce XSS. Like I said, like researchers have found internal XSS vulnerabilities in certificate authorities, which, as mentioned last time or two time, was it last time? I'm not sure. As mentioned previously on this lecture, are some of the most stringently audited and like some of the most stringent business requirements in auditing possible are like certificate authorities. And even those have internal XSS vulnerabilities in their control panels. So yeah, this is definitely not a thing that is like just small companies or just indie developers. Can happen to anybody. Easiest way to not do it is to not use insecure functions. If you never use .html, that's good. Don't use it. You don't have to use it. Like there is no rule saying you have to use it. You can just use .text or inner text or whatever your preferred method of setting text content is, and you avoid all of these problems. Okay, moving on because we're getting a bit late and I have more slides. Now for something harmless. I mean, at some point I'm overdoing the theatrics, right? It's obviously not going to be harmless because it's the lecture where we make you feel depressed about the state of information security. So this is the TU Graz logo. I'm sure you've seen it before. And I'm going to let a user upload this TU Graz logo to my website. So I'm an image hosting website, and I let users upload images. And like I filter by file extension, like I make sure it's actually an image. I don't let them just upload exe files to my website, that would be bad. I make sure it's an image, I make sure the file extension is correct, I make sure I serve it using the right MIME type so that the client knows that it's supposed to be an image. Like I'm being very careful. At this point, surely letting a user upload an image is harmless, right? I mean, it isn't, like, otherwise I wouldn't be talking about it. So this image in the slides is a vector graphic, SVG file. SVG standing for Scalable Vector Graphics. And for those of you not familiar with images, a vector graphic is, instead of how you would typically imagine an image working, like typically if you have a PNG file or a JPEG file, then below a bunch of layers of like encoding and compression, a JPEG or a PNG file is just encoding pixel data. So you have an image that is, let's say, 2000 by 1000 pixels, and then beneath some layers of compression and encoding, you have 2000 times 1000 pixels worth of data. So every pixel has some color value in like RGB and some alpha maybe if it has transparency, and that is image data. That's what's typically called a raster image because of the raster grid for a rasterized image, the raster grid for pixels. You think of it like a grid. Instead, vector graphics describe graphics as shapes instead of pixels. For example, how would you describe the TU Graz logo? Well, it is a red shape, polygonal red shape using these coordinates. Hold on, backwards. Polygonal red shape. No, that's still backwards, right? Polygonal. I give up. It's like this. Then it should be backwards, right? So polygonal red shape using these coordinates. I think I got that right. Something like that. And then like the text is like TU and like Graz, right? Text in black, polygonal shape in red. That is how you define a graphic in SVG or any vector graphics system, really. You define the graphic as a series of shapes of either characters or just polygons. And essentially, this lets your image scale infinitely. So you can take this TU Graz logo and you can render it at 100 times 50, or you can render it at 20,000 times 10,000. For example, if you want to print it on an A1 poster, you have to render it at some high resolution. And you can do that if it's a vector graphic. Because this shape is infinitely scalable. You can just take the coordinates and multiply them and they're still correct. And you will never have artifacts along the edges. You will never have the usual problems with like scaling curves where they start being edgy or like scaling characters where they start blurring. You don't have any of these issues because you're, instead of saving pixels, you're just saving shapes, describing shapes. SVG is the most widely used standard for vector graphics on the internet. It's based on XML. This is what it looks like. This is the TOGraph logo that is on the slides. If you start at the top, you have, created with Inkscape. There's a software for making these things. Some specification stuff. Okay, so the native rendering size is 800 times 400. So ID is called SVG2, whatever. And then we have we have a path. It has some font size, so that's probably the Graz text. It's the small font size. Then we have the big font size, which is the TU text. And then we have this path with these coordinates. That's the squares. And it's filled with this red color, EE2556, right? And then we have, oh god damn it. Yeah, I mean, okay. All of you that have read ahead have seen it. It's JavaScript again. Yeah. So, SVG vector files have the perhaps slightly short-sighted ability to run JavaScript code. Somebody thought that was a good idea. So yeah, SVGs can be dynamic, can react to user input, and can do that by running JavaScript. So any SVG file you upload, this image file, this image format can run JavaScript for some reason. So any image file, any SVG image file your user is allowed to upload, can contain JavaScript. Which, if it is served from your website, if your website is just storing the SVG file and then serving it back to the user, then your website is now vulnerable to XSS, right? Because your user can just upload this image and then link to the image. Now, I will note that browsers are not going to run any contain JavaScript if the image is just embedded. So if the image is just embedded in a website using image tags, the browser won't actually run the JavaScript, because browsers have gotten that clever at least. But if your image is being served from the web server, then we have the same problem that we had with the query string earlier, right? Where, well, Eve can just right-click, copy image link, and then send the image link to Bob, at which point, of course, the image does render with JavaScript and runs JavaScript. At which point you have a cross-site scripting vulnerability. Oops. Now, SVG has a question mark. Why does SVG have a question mark instead of a red cross? Well, because we need some kind of vector graphics format, and SVG is one of the only ones out there that are widely usable. So we kind of have to use it, but we need to take some precautions. I mean, the obvious precaution is don't let your user upload SVG files. Simple, right? Don't let them do that, at which point mostly safe. As long as no other format comes around that does weird things, maybe a whitelist, let them upload PNGs and JPEGs and GIFs and shit. Then we're probably fine. But sometimes you can't do that. If you're Wikipedia, then your business is letting users upload images, and Wikipedia has lots of SVG images. Does that mean that Wikipedia has trivial XSS vulnerabilities? If you link to the right image, you can take over somebody's Wikipedia account? No, thankfully not. We're going to talk about why in the next section, which talks about defense in depth measures, which are good to take, even if you're sure that your script is perfect. Because it probably isn't. That's a reality that we all have to accept, whether we like it or not. We are human and we make mistakes. And one great thing we can do is make sure that if we make a mistake, it bites us in the butt as little as possible. Thus the principle of defense in depth. Even if we're sure that there is no way that an attacker can include a script tag in our website, we're still going to take countermeasures against a potential attacker including script tags in our website. So that even if our initial assumption, nobody could ever include script tags, is wrong, we still have additional defense measures to fall back on. Let's talk about that. The first one is an incredibly powerful tool that very few websites use. It's called a content security policy. Essentially, it is your server, your web server, telling the browser, I don't want to have the ability to do everything. Think about that for a second. Usually, without a content security policy, the web server is allowed to do anything within constraints. Like, the web server is allowed to include a JavaScript file from evil.org. The web server is allowed to include an inline script tag, and the browser is going to run it. Because the early internet was a very permissive place. Now, in the modern day and age, with security vulnerabilities being in consideration, maybe that's not the best idea. So, with the content security policy, your server is telling the browser, I don't want the ability to do everything. I only want to be able to do these specific things, so that even if an attacker manages to include a script tag, the server has already told the browser, don't run inline scripts from me. I'm never going to send you an inline script. If you see an inline script, that's an attacker. Yeah, so CSP does whitelist-based filtering of JavaScript, style sheets, embedded frames, images, fetch and other data retrieval methods, and many, many more. It's incredibly powerful. Let's look at what that looks like. So an example is this. So CSP is a HTTP header. So this is something that is not part of the website itself, but this is part of the metadata that gets sent with your request or the response. This is an example. Let's look at it. So we have this long header with like these semicolons, and these semicolons separate what's called directives. So one directive would, for example, here be default source self. This is one directive. Then we have the semicolon. Then we have script source self, and then we have a semicolon. No, we don't. We have script source self, and then we have this URL, and then we have a semicolon. And then we have frame source none, and then we have a semicolon, and then we have object source none. So we have 1, 2, 3, 4 directives in here. What does each of the bits do? So each directive specifies first what are we talking about, and then it specifies what is allowed to run. So first we have default source, which is just a fallback. So any category, you will notice that there's like a bunch of categories in here: JavaScript, style sheets, frames, images, fetch, etc. I don't list all of these here. Anything that's not listed just falls back to this default source and just says, okay, fall back to just self. What does self mean? Only the current origin. So that means if I specify default source self, that means that the only thing that is allowed to run, for example, JavaScript, but also the only kind of image I'm allowed to include, the only kind of frame I'm allowed to include, etc. If I just have a default source self, I'm only allowed to include these things from my current origin. Even if Eve manages to sneak a script tag in there, it's not going to run. Even if Eve manages to sneak a script tag in there that has a link to evil.org, it's not going to run. The only thing that's going to run, careful, is stuff from my current origin. What does that mean? If Eve manages to upload a JavaScript file, for example, to my server, then Eve could run that JavaScript. Because Eve could specify, for example, if I'm a file hoster, Eve could upload a JavaScript file to my file hoster, and then just include a script tag with a direct link to that file. And now that file is being served from the current origin, from my server, would bypass content security policy here. But it does already lock a lot of attack avenues. It prevents you from including inline scripts, it prevents you from including scripts from outside hosts. Then we have a specific script source, which overrides the default source. So here we specify both self and we specify this other host. This is a useful feature. So we essentially include a whitelist. We say you can run scripts from either self, the current origin, or from this other origin static example.org. So for example, if all my JavaScript files are being served by this CDN, by this content delivery network that's really good at serving static files, then I will want to tell the browser, okay, you're allowed to run JavaScript files from this other origin, but not anything else, right? So here we have either self, me, or this static file server. And this is one of the big gotchas of content security policies because it whitelists the entire domain by default. For example, there are many of these useful things out there called code repositories. If you've ever run into a Node.js library, you've seen these. It's the thing where, oh, you can run our script really easily. Just include this script tag pointing at some public URL. And that's always going to include the latest version of our script, and everybody will be happy. if you whitelist any kind of publicly accessible script repository in your CSP, then your CSP is pointless. Because that means Eve can run any JavaScript that is hosted on this public repository, which anybody can upload files to. Like if your CSP includes, let's say, api.google.com, or what's that Node.js one called? Deliver.js or whatever it's called. There's like one of these like big public ones, like deliver.js, or whatever. If any of these are whitelisted in your content security policy, then it defeats your content security policy because, well, Eve can just upload the attacker script there and run it, and your CSP is pointless. Also interesting, you can also specify none if you don't need a feature. For example, here we have absolutely no plans of using iframes or other embedded objects, so we're just going to turn them off. Because obviously, like, we've only been talking about JavaScript, but there are many, many, many different things that Eve might embed in a website. For example, if JavaScript is not allowed, well, we might embed an image link, potentially to a malicious SVG file, for example. Or we might include an iframe embed that looks like your login page, for example. I might embed an iframe instead of the direct message content. I might embed an iframe that makes the user think, oh, I need to log in to view the message. And I guarantee you, like, half the users are going to log in. That's a conservative estimate. So if you don't need these features, just turn them off. Like, no way to inject an iframe if iframes are disabled for the page, because the content security policy says no iframes. Yeah. There's a really useful tool by developers at Google called the CSP Evaluator, which lets you, well, essentially you just take your content security policy and you copy paste it into the thing and you click evaluate, and the thing is going to tell you, is this secure or not? What are potential problems with this? For example, if you whitelist jsdeliver.com and you plug it into the CSP Evaluator, the CSP Evaluator is going to throw up a red exclamation mark and go, you are whitelisting a public code repository, your CSP is pointless. Or if you, for example, have a very permissive script source, it's going to yell at you, that kind of thing. Incredibly useful to use. I use it whenever I design CSPs. It's really cool. What else do we have? Because, as mentioned, CSP has a big problem, which is user uploaded files. If you let your user upload files to your website, then that bypasses CSP because it's being served from your website. The idea is, well, why are we serving it from our website? I've nicknamed this strict origin separation. I don't think this has like an official quote-unquote name, like widespread name. I've called it strict origin separation here because that's kind of what it is. Essentially, all of these web protections, same origin policy, cross-site content security policy, all work based on origins, right? They all work on, you whitelist certain origins, you're allowed content from the same origin to access stuff, etc. The idea is, well, let's just use that. There is no rule saying that we have to serve all of our data from the same origin. Instead, split in 2, split in 3, split in 4, split in whatever. Basic idea, we have 2 origins, 1 and 2, A and B here, and we say, okay, origin A is the one that serves the secure data. So origin A is where your session cookies go, origin A is where you request some like authenticated APIs, like if you want to upload a file, you talk to origin A and call the upload file API. Anything else that's interesting goes there. All of our websites go there, like all the static content goes there. It's all trusted. And then origin B is for all the untrusted data. So if you upload a file, that file gets served by origin B, not by origin A. Anything else that seems shady goes on origin B. And that way, even if the attacker gets cross-site scripting, even if the attacker uploads a malicious SVG file and the links to it, attacker doesn't gain anything because origin B is not origin A. So even if you're on origin B and you have a malicious SVG file and the user clicks on that malicious SVG file, the user runs your JavaScript, it still doesn't gain you anything because the origin B JavaScript is the same as the evil.org JavaScript. It can't actually access the data on origin A. And then CSP can explicitly whitelist origin B when you need it. For For example, if you're including only images from users, then you can use image source and whitelist origin B, but leave script source on self, for example. And that way, scripts from the user server cannot run, but images can. That kind of thing. Let's look at that in practice. I picked up a random website that looked like probably has decent security. At this point, it's GitHub. I'm looking at GitHub. That's the current CSP. You can see it's a bit more complex than the toy example we've looked at so far. But this is the current CSP for GitHub's front page. Bunch of stuff in there. Interesting stuff. They have a really, really restrictive script source. Like their script source is restricted to just github.githubss.com, so just their script CDN, which means nobody, it's impossible for you to get XSS on GitHub's front page. It's that simple. Like the only XSS you could get on GitHub's front page is if you manage to upload a JavaScript file to github.githubss.com. And if you do that, then you've got bigger problems because you can just replace the existing like actual website. But like any kind of inline script tag isn't going to run, any kind of external script isn't going to load. The only stuff that's going to load is that stuff. Yeah, all the user-generated content, if you've ever looked at like the raw view for your repository, for example, any files in your repository, if you click view raw, you're going to end up on this GitHub usercontent.com origin, which apparently has like sub-origins, like for example, viewscreen.github-usercontent.com or render.github-user-content.com, whatever. So yeah, even if you somehow sneak a script in there, even if you like upload a malicious SVG file to your repository and click view raw and you send that link to Bob, then all you're doing is sending a link to a JavaScript file on github-user-content.com, which actually cannot access any of the data from github.com. So even if you upload your repository, malicious file to your repository, link to it, the attack we described earlier, it doesn't do anything because it still cannot look at GitHub's cookies, it cannot make any requests to GitHub, etc., because it's on github-user-content.com, which is not trusted. So yeah, strict origin separation is what I called it. Essentially, you just use different origins and make use of SOP that way. Right. That's the main content for today. Now I have a thing on the slides that I called Web Dev Grab Bag. This is kind of similar to the thing that somebody prompted me for during the lecture. Stuff I want to rant about, but I didn't fit it in the lecture somehow. But I felt the need to actually put it on there because it's super common. But it didn't fit the narrative, so it goes at the end in a bit more of an unstructured manner. From last time, this is how JavaScript works, fundamentally. Your web server tells the browser, hello, here is a program, please run this program while displaying the website to the user. Operative word, please. JavaScript is voluntary. There is no law of physics that requires a user of your website to run your JavaScript. In particular, an attacker does not run your JavaScript. If you put a check in your JavaScript code, that check is irrelevant to an attacker. An attacker can make any request with any parameters in any order that the attacker wants. This is like a thing that developers always get wrong. Like you see this so often in websites. Like, for example, not maybe with admin features tend to be a bit more secure, but for example, like premium features. Like you have some subscription service, like some pro mode of your website, right? And then in the JavaScript code on the client side, you have some check that goes like, yeah, if is premium user, show extra button. That is irrelevant to a malicious user. That is irrelevant to anyone that can press F12 and look at your website. But people do that constantly. Like they just disable features on the client side, but if you just show the button and click it, it works. Like all the APIs on the server don't check that you're actually a premium user. They just trust that a non-premium user could never make this request because, well, the button is hidden, right? How could you click it? By looking at the JavaScript and just removing the check. Like, JavaScript is voluntary. It runs on an attacker-controlled machine. The attacker can do whatever the attacker wants with your JavaScript. The attacker can read your JavaScript and figure out what APIs to call. Or the attacker can just change your JavaScript and remove your security check. If your security check is in JavaScript, it's not a security check. Like, anything that runs on the client cannot ever be a security check. That simple. People constantly forget this. So I really just wanted to stamp this one home. Your attacker is not running your UI. The attacker is just making requests to your server. And those requests might look like they're being sent from your UI because they might be indistinguishable from genuine requests. But the attacker is not using your UI by necessity. Okay? Yeah, the examples, admin features hidden on the client side and the server side checks. I've seen this one in practice once. Also, really common one, like quantity limits that are only enforced by the UI. Like, for example, any user is only allowed to order up to 2 of these. And then there's like a JavaScript check that says, oh, you're not allowed to click plus if it's 2 already. And then you just remove the check and you order 5 and it still works. Exactly this. Like, an attacker doesn't care about your JavaScript. Unless the attacker wants to care about your JavaScript. Like, if the JavaScript is useful to the attacker, then the attacker is going to care. But if your JavaScript is constraining the attacker, then the attacker just turns it off. Or changes it. Or, well, yeah, circumvents it. Like, it runs on the attacker's browser at the attacker's leisure. Is the point. The attacker can send any request in any order with any parameters. Do not rely on any ordering enforced by your JavaScript, because your JavaScript doesn't constrain the attacker. A bit of a pain point because it happens constantly. Next one, Eve might be pressing the buttons for Bob, is what I call this one. If you're designing UX, if you're designing user experience, you're typically thinking of it in terms of workflows. You might not be thinking about it in terms of formally in terms of workflows, but you're essentially thinking about it in terms of workflows. What does Bob want to accomplish? Bob wants to, for example, reset his password. And you design a reset password flow. Well, what does a reset password flow entail in the modern world? It entails some kind of confirmation email. Like you validate that it's actually Bob using some external means, and then you re-establish access to the account by resetting the password. Straightforward, right? What if the person clicking the buttons on your website is not the same person that is reading your email? Like, that's probably not something you thought about. Many developers don't think about this one. You just think of it in terms of, oh, Bob wants to reset his password, so Bob goes on my website and clicks reset password, and then Bob reads the email, and then Bob clicks on confirm. Let me change the story. Eve goes on your website, clicks reset password. Eve enters Bob's email. And Eve enters a new password. I've seen this in practice. And then Bob gets an email. And the email just says, hello, this is website. Please click to activate your account. And there's a link. And Bob clicks the link, at which point Eve gets access to the account. Don't do that. You have to consider, it might be you might have a situation where Eve is doing some parts of your user flow that are publicly accessible. If you're, for example, the reset password dialog is publicly accessible. Eve can access the reset password dialog and enter whatever email is desired. Could be Bob's email. And then Bob is going to get an email from you. And all of your authentication, all of your out-of-band authentication, the email verification, only kicks in once it's Bob clicking the link that has the one-time token or whatever in the URL. The only moment that your out-of-band authentication, the email confirmation thing, actually confirms anything is the moment that you are seeing that token in the URL. So this flow, for example, where Eve clicks reset password, Eve gets to choose the password, and then Bob has to confirm, is broken. It's broken even if your email is descriptive. And it's even more broken if your email isn't descriptive. Like, you need to consider, if you're designing an email that is sent to a user in response to some action, you cannot assume that the user is actually the one that initiated the action. Might be Eve. Might be an attacker initiating the action, and now the attacker needs the user to confirm it. Your email has to describe what am I confirming, and has to be very clear about it, because users are very trained to just click links in emails. If you just send a generic email, hello, this is website, please confirm your account, link, people are going to click on it. And this is, again, something I have used to break a website in practice. It had exactly this flow. Like, Eve clicks reset password and gets to choose a new password. And then Bob gets a confirmation email, please activate your account. And then Bob clicks it, because of course Bob clicks it, and then Eve now has the password for the account. Awkward. So yeah, consider this when designing user experiences. There's a security factor to this. It has to be clear to Bob what Bob is doing. And also you need to consider, at what point am I actually sure that it's Bob? At the point where the email gets clicked. Like, at the point where the link gets clicked, you're sure that the browser that opens that link is Bob. Or as sure as you can be. At any point before that, might not be Bob. Could be Eve, could be an attacker, could be malicious input. Could be malicious input even afterwards. But up to that point, it's not input you know is coming from Bob. So yeah, that's another one that's very common. People design their user experiences and they forgot that attackers exist. Yeah, try to dig into what your system is doing. This one's a bit of a long shot. You see, this shouldn't be something you should have to do. That's what makes it slightly depressing, to put it in the lecture. Like, web frameworks, cryptographic frameworks should be a lot better at the stuff that I am talking about in this lecture. Not the injection stuff, like not the technical stuff. They're pretty good at that usually. But the misuse resistant stuff. The stuff that I'm talking about, it's hard to get this wrong. Like, you will remember, like an hour ago I talked about prepared statements versus SQL escaping, sanitization. And I said, don't do sanitization because it's very easy to just forget once, and then everything's broken. Instead, use prepared statements because it's impossible to forget. Like, if you use prepared statements, then you are safe. Assuming that you don't put like input in the prepared statement, in which case, of course, but like, it's very hard to shoot yourself in the foot if you're using prepared statement, and it's very easy to shoot yourself in the foot if you're using screen escaping. And that's why I said use prepared statements. And frameworks should be doing that. Frameworks should be going, how easy is it to misuse this function? I should design my function so it's harder to misuse. But frameworks don't do that yet. We're not there yet. So for now, you kind of have to. If your framework provides a feature, how does it provide this feature? What guarantees does it provide? How does it indicate unexpected scenarios? For example, real world example, this was a Node.js web server, provided with some fancy framework, and that framework was providing session authentication. So essentially, whenever you called an API, you would specify a session token, and you would specify the API handler you wanted to call, and then the framework would check your session token and would then hand off to the scripted API handler, and would then package the result up and send it back to you. All very nice, very fancy. How does this session framework indicate that your session token is invalid and you are not logged in? Now you might think, well, obviously it's going to throw an exception. Obviously you would be mistaken, because this is the lecture where we make you feel depressed about the state of cybersecurity. Instead, the session framework indicates this by setting a variable on the returned object that is prepared and passed to the function, and it sets this logged in as value to nobody. This could have other values, like this could have like user, this could have like admin, or if the session token is invalid, set to nobody. Now the API handlers, the stuff that is actually scripted by the final developer, the app developer, did not check this value. Why? I mean, I don't know. I just know that this was the bug. Like, I was sending API requests, and I could see that if I just removed the session token, I was still getting valid data. The only thing that changed was this value provided by the framework, which is logged in as, which changed to nobody. But the API handlers never checked this value. Maybe the developer thought, well, I mean, obviously, like if authentication fails, it's just going to throw, right? Like, obviously, I mean, that's what you would think a sensible framework might do. Didn't. It just assumed, well, the developer is going to check this value, right? But the developer forgot, or didn't know they had to. Who knows? Misuse resistance, this is not. It's very easy to misuse this. You can just forget the check once. Like, even if you're aware you have to do the check, like, you're writing 500 APIs. You're going to forget on one of them. Like, it's just going to happen. So yeah, anybody can request any API path without authentication. Awkward. Yeah, another one, consider potential attacks. What guarantees does your framework actually provide? Just because you're using an authentication framework, it's not magic. It does something. What does it actually do? What does it guarantee you? It guarantees you that it's the same user that got the session, for example. Does it guarantee you that that user is an admin? Maybe, maybe not. Think of potential attacks. That just goes for any software development, really. Take some time, look at your code like an attacker would. Like, your practicals for this lecture have been pretty good practice for that. Look at your code and think about, if this is a hacklet, somebody tells me this is a hacklet and I'm supposed to break this. What do I do? And then try it. Or at least get to the point where you're yourself very certain that you couldn't. Or if you could, well, then fix the bug. This is essentially a do-it-yourself version of what I described earlier about pen testing and red teaming. This is essentially you pen testing your own software, which is not optimal because you yourself are obviously biased when you're looking at your own software, because you're reading your own software while understanding what it does. And somebody else that reads your software is going to look at it with completely different eyes because they don't understand what it does yet. They're going to learn what it does, and while they're doing so, they're going to look at it in ways that you never would. So no amount of looking at it yourself is going to beat third-party or second-party code review. Somebody else looking at your code is incredibly valuable. Consider doing it when you're doing security critical stuff. I realize it's not that easy to find somebody to look at your application framework. But yeah, try to consider what an attacker might try. Try to avoid it where possible. Apply defense in depth. You should have a content security policy for your website. There is no reason not to in the modern day and age. If you can afford it, you should consider domain separation if you do file uploads or whatnot. Do as many things as possible within reason. I mean, nobody can sadly be perfect. What's the last one? Yeah, design securely. I mean, I've been talking about this one for the entirety of the lecture already. It's a truth that very, very many people in computer science do not want to accept, and they really should. Some aspects of computer science are a bit problematic in that regard. You are a developer. You are human. You will mess up. It's that simple. As you keep developing, the probability of you introducing a security vulnerability approaches 1. Just by virtue of you being human. Okay? So when somebody else makes a mistake, the solution is not point and laugh, as it always is on the internet. It shouldn't be. Somebody else messes up, the solution is, why did they mess up? How can I make sure the same mess up doesn't happen again? This is what I'm talking about with misuse resistance. If somebody messes up, if you're writing some library and you notice a user messing up your library, like they're just using your API wrong, and that's why it's insecure. Don't like tell the user, well, you should have read the documentation. Consider, how can I make it harder for somebody to make this mistake? Like, just make it harder. Figure out how could people misuse my code. Make that harder. Like, you could go like, oh, the user specified a private key where a public key is supposed to go. How dumb. Or you could go, wait, somebody passed a private key into a field that's supposed to be a public key. Maybe I should like have separate types for my private keys and public keys. That could fix that. Like, instead of just having like 32 byte arrays of like binary, like std array character 32, maybe you should have like semantically different types, and one's called private key and one's called public key. And then suddenly people can't make that mistake, right? Because you're preventing them from doing it. Unless they go out of the way, of course. But like within reason, you're preventing somebody from making that mistake by design. It's good. You should be doing that. Solution is very rarely point and laugh, because you too are going to make that kind of mistake at some point. I'm very sure of it. You probably already have. Yeah, try to make it harder to make mistakes. Isolate critical functionality. That's very good if you're writing code yourself. The simpler the code is, the easier it is to make sure it's not broken. And yeah, design security relevant code to be misuse resistant. It just goes for any code you design, really. Make it hard to misuse code, because it's not always going to be you changing the code. At some point, somebody else is going to have to work with that code. Make it hard for them to mess up as well. And yeah, computer science is very bad at this, sadly. We're getting better at it. Like, things are slowly progressing. I don't want to be like completely depressing here, but yeah, sadly the standard approach to information security mess ups is very much still point and laugh. Or if you're the person in charge, yell at person making mistake. Looking at you, Mr. Torvalds. Right. That closes today's lecture. We have one more networking lecture, and as I said at the start of the lecture, the first lecture, I'm not quite sure what we're going to put in that one, because I intentionally left it open as like kind of a grab bag of stuff that people want to hear about. So I grabbed a bunch of things that were mentioned in the first lecture, or have mentioned to me since. Privacy and metadata was one that was mentioned. Gonna see what we can do about that one. It's a bit of a wide subject, but I'll try to cover it. VPNs are mentioned. We're gonna talk about how VPNs work. We're gonna talk about the tool chain, the kind of tools you can use to actually do this stuff in practice, and what they do, very briefly. Wireshark, that should be Wireshark. Yeah, Nmap, DevTools, etc. Gonna talk about that stuff. And then finally, obviously, this is the part, like I collected some topics at the start, and this is the end, and before I let all of you go, I am going to collect some more topics. Yeah, you can, somebody was quick, you can already vote on type on your Mentimeter app, topics you want to hear next week, because I have not yet made that many slides for next week, and I want to make more slides, so throw me some keywords that you want to hear more about. Could be stuff we've already talked about, could be other stuff that's like security adjacent. I'll pick some out of the grab bag and talk about it. Log4j problem. Yeah, we can talk about that. I always like yelling at Java for being bad. Yeah, we can talk about Log4j. Responsible disclosure. Yeah, we can talk about that a little bit. We'll see. I'm gonna have to say I'm not a lawyer, so yeah. It's a bit more of a policy thing, but yeah, we can talk about responsible disclosure and what it looks like a little bit. We got anything else? Word cloud. Nobody? Okay. Well, if any of you come up with more stuff you want to hear about next week, you can still tell me. I mean, I'm on Discord. You can reach me. If it reaches me within a reasonable time span, I'll try to put it in the slides. And yeah, next week is going to be grab bag of stuff we haven't talked about yet. Log4j responsible disclosure is going to be in there. Privacy and metadata, yep. VPNs, yep, going to talk about how it works. Toolchain, we're going to look at some actual tools and how you can use it, like what they do in practice. Yeah, and that's it for this week. We are done. We're already over time anyway by like 2 minutes. I've actually used my entire lecture slot for a change, mostly because I started ranting in the middle. And yeah, we're done. Thanks for attending Information Security. I hope you're not completely depressed, though if you are, you're not entirely wrong. And I will see you all next Friday for the last of my solo lectures. And then the Friday after that, there's some joint thing going on. So yeah, I will see you all next Friday. Send me a DM if you have more topics you want to hear about. And have a good practicals, I guess. Bye-bye.